Hello, in this video we're going to look at balance torques worksheet number 1 and go through some problems together. It says in this worksheet we have a meter stick that's hung from a string and bounces at the 50 centimeter mark. We want to calculate where would you place a second mass to balance the weight. Draw the answer after you calculate it. It asks in part A, where would you place another 200 grams? Now the first thing we're going to do is we're going to calculate the torque, which is force times radius, from the 200 grams that is currently on the left-hand side of this meter stick. The meter stick is supported by a string at the 50. Now to calculate the torque, we're going to multiply the force and the radius. The force is the 200 grams, and the radius is the 10 centimeters. When we multiply those together, we get a torque of 2,000. Now the idea here is that the torque on the left and the right are going to be the same. We are in what we call equilibrium. So therefore, the torque on the right-hand side is also going to be 2,000. We have a torque of 2,000 on the right. The force on the right is going to be another 200 grams. And we are going to solve for the radius. Now, whenever you're solving an algebra problem like this, and you have these two things multiplied together on the right-hand side, we have 200 times r. To get r by itself, we always divide by the number next to the variable. In this case, we're going to divide by 200 to get r by itself. The 200s cancel out on the right-hand side, and we get a radius of 10 centimeters. Now that does not mean we are going to place the second mass at the 10 centimeter mark of the meter stick. What it means is we're going to be 10 centimeters further than the string. So we're going to be 10 centimeters on the other side of the string, or we're going to be at the 60 centimeter mark. We're going to draw our mass in that spot. Continuing on, letter B, it asks, where would you place a 50 gram mass if we have 100 grams on the left-hand side? Again, we solve for the torque by multiplying the force and the radius. The force in this case is 100 grams. And the radius is 10 centimeters. Again, the radius is how far we are from the fulcrum. When we multiply 100 times 10, we get 1,000. This means that the torque on the right-hand side must also be 1,000. Again, we are using this idea of rotational equilibrium, that the torques are equal. Now the force on the other side is 50 grams. Yes, where we would place 50 grams on the other side to balance. And again, when we're solving for r, we divide by the number next to the r. So I'm going to divide each side by 50. Here the 50s cancel out, leaving us with r. And we get an answer of 20 centimeters. This means that we are 20 centimeters from the string. 10, 20. 10, 20 centimeters from the string. So we're actually going to place this mass at the 70 to balance it out. Now what I want to point out here is that the mass on the left is twice what it is on the right. That means that the leverage on the right must be twice what it is on the left. If you have twice the mass on the left, that means to compensate, you must have twice the leverage on the right. Next problem in letter C, it asks, where would you place a 200 gram mass to balance the system? Again, we're going to multiply our force and our radius. My force is 50. My radius is 40. I get 2,000. That means that the torque on the right must also be 2,000. My force on the right is 200. Whenever we're solving for r, we divide by the number next to the variable r. The 200s cancel out on the right, leaving r by itself. When I take 2,000 divided by 200, I get 10 centimeters. That means we need to place this mass 10 centimeters from the string. We're at the 60. Notice that in this case, the mass on the right is 4 times bigger than that on the left. That means that the leverage on the left must be 4 times bigger than that on the right. So the mass is 4 times bigger on the right, the leverage is 4 times bigger on the left. And the last problem on the first page, we have 2 different masses on the left-hand side. We want to know where would we place a 200-gram mass on the right to balance it out. Now in this one here, we're going to solve for the torque from both masses. The first mass is 50 grams, and the first radius is 30. And this gives us a torque of 1,500. For the second mass, we have a 100-gram force at a distance of 10 centimeters. This gives us a torque of 1,000. So we have a torque of 1,500 from the 50 and a torque of 1,000 from the 100 to give us a total of 2,500 for a torque. This means that the torque on the right must be a combination of both of them. The torque on the right must be a combined 2,500. The force on the right is 200 grams. Again, to solve for the radius, we divide by the number next to it to get rid of it. And we get a radius of 12.5 centimeters. So that means that we're a little more than 10 away from the string. We're going to place our mass right there, and it is 200. Now on the second page, we are very similar here. Well, now we have a seesaw. In the first problem on the second page, it says, as a child, you used to ride a seesaw. Still do, perhaps. If your friend, who happens to weigh 750 newtons, is sitting 2.5 meters from the fulcrum, how far from the fulcrum should you sit if you weigh 900 newtons? Make a calculation, and then draw yourself and state the distance. So just like before, we're going to solve for the torque from your friend. Your friend has a force of 750 newtons. The distance of the friend, remember, is always measured from the fulcrum. The friend, if we look at her picture, is 2.5 meters away. You can also see it up here, it's 2.5 meters. This gives us a torque of 1,875. Now the torque on the right must also balance that out, must be the same amount of torque. So the torque on the right must also be 1,875. The force of the person on the right is 900 newtons. To solve for r, we always divide by the number next to the r. When we divide 1,875 and 900, we get an answer of 2.08. This would be units in meters. Now remember, this 2.08 meters is how far we are from the fulcrum. So we're a little bit more than 2 meters away. We can draw our person in here. For the very last problem, it says we have a 750 Newton dad, sits at one end of a 6-meter seesaw, pivoted at its center, and his 240 Newton son sits at the other end. Where would his 650 Newton wife have to sit to balance the seesaw? Make a calculation and then draw in mom. Now in this problem here, we're going to solve for the torque from the dad first. Dad has a force of 750 newtons. Dad's radius, again, is how far he is from the fulcrum. He is 1, 2, 3 meters away. This gives him a torque of 2,250 Newton meters. We do the same thing for the sun. We're going to find the torque from the sun. His force is 240 newtons. And his radius, again, how far he is from the fulcrum, is also 1, 2, 3 meters away. This gives the sun a torque of 720. Now these torques are not the same, and therefore it's not going to balance. Mom is going to balance the seesaw. Now to figure out how much torque mom needs, we need to see where we need extra torque from. You see, dad has more torque than the son, and therefore mom has to sit on the same side as the son. We need both sides to be 2,250. So how much torque must mom produce to compensate for the deficiencies in the torque of the son? Well, to figure this out, we're going to subtract the 2. Mom needs a torque of 1,530 to give a total torque on the right the same as the torque of 2,250 on the left. So mom's torque is 1,530. Her force, if we look up here, her force is 650. To solve for r, we divide by the 650. They cancel out on the right. And we get that the radius is 2.3 meters. Our final step is to draw mom on her seesaw, and she's a little bit less than 2.5. So she'd be located right about here. So again, the main idea of this activity is to make the total torque on the left and the right the same, and then to solve for the radius of the unknown value.